Temporal subgraph isomorphism. Basically, what the problem is when you have to find subgraph isomorphism between dynamic graphs, graphs that change with time. The existing solutions that solve this problem use an aggregated model with time-stamped edges, and they did not maintain the temporal order of the dynamic graphs. Where Oberoi solved this problem, he used a snapshot-based model, which basically treated each snapshot of the dynamic graph as a static graph, and he used the VF3 algorithm to find subgraph isomorphism between these snapshots of the dynamic graph. And this, of course, allowed him to maintain the temporal order of the whole dynamic graph. Now, how is this different from the previous solutions? The previous solutions condensed the whole dynamic graph into one static graph. Basically, they took the average values of the edges and use an average value for each edge in the static graph. And this would, of course, you would be losing intricate details about your dynamic graph. Where over used a snapshot-based model, you maintain these intricate details and you can find accurate subgraph isomorphism between each snapshot of the dynamic graphs. You would also be maintaining your temporal order, so that is also a plus in this solution. Now, how is this better from the previous solutions? If we talk about time complexity, Oberoi's algorithm was compared to two other algorithms, which are the temporal RI and Mackey's algorithm, both of which use an aggregated model to solve this problem. Now, Oberoi's solution stood in second place, and the best time complexity for him was n square, where n is the number of nodes in your dynamic graph. But the main aspect where Oberoi's solution shines is the accuracy of the graph. Basically, you can find accurate subgraph isomorphisms between each snapshot of the graph, and it is especially applicable in places where temporal relationships take great precedence. Now, Mehdi will be talking about how the code is run.
So this is how we run the code. We made a bat file which had the compiling G++ code as well as the inputs. So the inputs. Okay, I'll explain the inputs in the next slide. Okay, so our inputs for this code were, firstly, we went to the data set, and for the target graph, we used the email 50 days data, and we took out the first five snapshots of that graph. For the target and for the pattern graphs, we went to the two nodes with the five snapshots first graph, G1, and we used the five pattern graphs there, and we did not increment our window. And then, so this is the output. The output is I've mapped the output. So first I'm going to explain it without the map. Basically, as you can see, H0 over here is H0 is our first pattern file. So in H0, there's a relation between A0 and A1, both of which are nodes. And the relation of A0 and A1 is mapped in the temporal graph as G0 in the first temporal snapshot as A925 and A592. Similarly, the one for the second pattern graph is found in the second temporal graph, in the second target graph, and so on for these five graphs. So for these five pattern graphs, coincidentally, we have the same relation and the same solution. So the time to compile the solution was 0.01 seconds, and there's one solution for the entire pattern graph. Okay, so this is it mapped graphically, visually graphed. So in H0, H1, H2, H3, and H4, which are five pattern graphs, it is mapped as A1 to A0 to A1. And similarly, it is mapped onto the target, it is found in the target graphs G0 to G4 as A592 to A927.
So today I'll highlight key insights for figure number 3 and figure number 4. So figure number 3, let's start with figure number 3. Figure number 3 is graph profile, which is showing passing variety. So the figure compares the interaction patterns of Argentina and Spain during their final match. Spain's graph profile reveals a higher diversity patterns and a broader range of passing sequences than Argentina. This complexity, measured as higher entropy, indicates Spain's less predictable and more adaptable style of play, correlating with their stronger performance. So let's move on to figure number 4. So in figure number 4, there's one figure showing transition profiles and the other one is showing restricted transition profile. We examine how the how teams transition between interaction patterns. The transition profile consider all pattern changes, while restricted transition profile excludes self-transition, focusing solely on shifts between different patterns. Spain displayed a richer variety of transition, demonstrating dynamic adaptability This diversity gave them the offensive edge. So moving on. In conclusion, higher entropy or greater variability in passing networks lead to better performance, and temporal models can enhance performance analysis in team sports, offering insight beyond the traditional static statistic models. Thank you.